Hi everyone, welcome to the Earth Science Regions Review podcast series created by the Hommocks Middle School Earth Science Department. Today we're going to be talking a little bit about the universe. Well, what is the universe? Basically everything as we know it. It's going to be our galaxies, our stars, our planets, our moons, our comets, and even energy. Well, how old is the universe? Well, scientists don't know 100% sure, but they have it kind of nailed down somewhere between 13 and 15 billion years old, with the average accepted value right now somewhere around 13.7 billion years old. Well, how did the universe form? There's a couple theories out there, but the leading theory is what we call the Big Bang Theory. Basically what this states is somewhere around 13 to 15 billion years ago, everything as we know it was crammed into a small location in space called a singularity. There was so much material crammed into that little spot that the gravity got so great and it exploded. Expansion of this explosion was originally somewhere around the speed of light. And at that very moment, everything as we know it was recreated, including time and space. It took about 10 billion years for things to calm down and start to cool off. That's when hydrogen gas started to form. Well, pockets of hydrogen gas in the space are what we call nebula. They're kind of the baby factories for stars. Well, in order to get stars, you need hydrogen gas. In order to get a galaxy, you need a big collection of stars. That's how the universe started forming. That's how all of our galaxies started to form. And that's really the origin of where our solar system was going to come from as well. Well, how was this theory created? Well, we need to talk a little bit about energy here to fully understand it. This is your electromagnetic spectrum. The left-hand side, gamma rays, X-rays, and ultraviolet, invisible light. On the right-hand side, you have infrared, microwaves, and radio waves. Left-hand side are what we call decreasing wavelength. Right-hand side, we have what are called increasing wavelength. The most important piece of electromagnetic spectrum out of this chart is going to be visible light. And the reason why? We can see it. How do we know we can see it? We can see the colors of the rainbow, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Well, light energy from our sun, light energy from stars and galaxies, they travel in waves. Okay? And the way that we can identify if an object is moving towards us or away from us is what we call wavelength. And that's basically the distance from top of one wave to top of the next. Now sometimes those waves can be really stretched out. That's what we call long wavelength. Long wavelengths are not really that harmful for us because you don't get hit with as many waves per unit time. So long wavelengths would be a good example. That would be radio waves. Okay? And you have such a long wavelength in between each one, not too harmful for us. Well, you compare that with a short wavelength, like your ultraviolet. We know it can happen to too much exposure to ultraviolet. You end up getting sunburn. Why? The shorter wavelength, you get hit with more waves per unit time. Short wavelengths tend to be a little bit more harmful to us. So the way we categorize or organize our electromagnetic spectrum is by wavelength. Well, what scientists could do is that they can look at light from distant stars and distant galaxies through what we call a spectroscope. So basically what happens is the light produces what almost like a fingerprint. Now you look at the fingerprint in the standard spectrum. Let's just assume that that's a fingerprint for the element hydrogen. Look at the spectrum from a distant galaxy. The spacing of the lines is identical, but if you notice that the spectrum from the distant galaxy, they're shifted to the red end of the spectrum. This is what we call a Doppler redshift. Now this is kind of the evidence that supports the Big Bang actually occurred. Because if objects are moving away from us, the wavelength gets stretched out away from our eye. The wavelength gets longer. The color red is associated with a longer wavelength. If things are moving away from us, we call that a redshift. The exact opposite of that would be a blue shift, a Doppler blue shift. Objects coming towards us, okay, those wavelengths get compressed against our eye. The objects moving towards us called a Doppler blue shift. And that doesn't happen that often in our universe. Mostly everything that we know produces some sort of red shift, which supports the idea that the universe is still expanding. So this galaxy is going to be red-shifted, so it's going to be receding or moving away from us. So when we talk about red shifts, okay, red shifts or the Doppler effect is going to support the Big Bang Theory. The universe is still expanding. Okay, that's it for now. Thanks.